Hi folks, welcome back to Math with Captain Rod. Making this video here to help you out with your homework. So we're going to look at the first maybe 4 problems on your Unit 4 homework here. And this first one here is just about calculating torque. So remember, torque is force times distance. I like to use this letter for torque, Greek letter tau, so that we don't confuse it with tension or temperature. So torque is force times distance, but the important thing is they have to make a right angle. So in this problem, right, look at the first one. We have a force and a distance. There's our distance, makes a right angle. Should be virtually nothing to that. It's perfectly acceptable to just give the torque in inch-pounds. And don't forget a direction, right? The direction for that one is counterclockwise, which generally is considered positive for torque problems. All right, next one here, when you're dealing with this one. So this force, this 20-pound force, has a line of action, right? That force can be considered to be acting anywhere along this line. So method number 1 for handling it is you can take the 20-pound force times this distance right here where it makes a right angle. Because the force and the distance, they have to make a right angle. Now, the other way you can handle it is this. Or actually, let me back up though. In this triangle right here, the hypotenuse of that triangle is the 4 inches. And you should be able to figure out this angle to then get to that distance. Now, the other way to handle it is to take this force, which makes a 65-degree angle, and break it into components. I'm going to draw it like this and this. This component does not create any torque because it goes right through this point. You want this component times this distance. And this angle right here would be 25 degrees. And again, that's creating clockwise torque. Get rid of some of these things. Okay, the third one here. Now this force right here, look at the line of action goes right through the bolt. That should give you an idea of what the answer to that is. Just ask yourself, is this force going to turn that bolt or not? Yes or no? Okay, this guy right here, I would break it into components, calculate the component this way and the component this way, take this force times this distance, and you are good to go. All right. And don't forget to attach a direction, clockwise or counterclockwise. Next on the list, calculate torque about O. So if you're calculating torque about this point, you've got 75 newtons times this distance, both given, 100 newtons times this distance. Now torque, you have to remember though that generally speaking, counterclockwise is considered positive. So one of the torques is positive and one of them is negative. I'll let you decide which. The 100 newtons, the line of action, goes right through our point of interest. So that should tell you about how much torque it produces, about O. The next one here is virtually the same problem. It's just there's this 70 Newton force added in. Ask yourself, well, how much torque does that 70 Newton force create about O? And hopefully you'll come to a conclusion about that. All right, moving on. Okay, for each, let's see, each force is 100 newtons. Find the net torque about A, B, C, and D in Newton meters. I'll do one of these. I'll talk about B. So if we try to calculate torque about point B, I like to put like a green dot there. The first force here does not produce any torque about B because it goes right through B. Okay, then we have this force, 100 newtons times this distance, and it's clockwise, so we would attach a plus sign to that. Second force, 100 newtons times this distance, and that one's counterclockwise. And again, remember, clockwise is positive. That should be enough to get you through these problems. Moving on. Timmy, yeah, young Timmy, okay. So we're going to imagine that this is a light beam. It's in equilibrium here. And the idea is to draw a free body of the system. I would define the system like this. Just include Timmy and the bear in your system. Whoops. And then I don't want to complete it for you, but you know, you You should have a force vector for Timmy's weight, another force vector for the weight of the bear, and then there's a contact point right there. So get your free body complete for the beam. That free body should have 3 forces. Now, if the beam had a reasonable mass, we would have to include a force vector for the weight of the beam. But this one says a light beam, so we'll ignore the weight of the beam. Okay, then what you want to do is write a torque equation. And this point right here would be a good point to use because the force at the pivot point there won't show up in that equation, and you should be able to calculate this distance, you know, call it x or something like that, and you'll get it out of a torque equation. Oops. Let's go ahead and do one more. Okay, number 5. So let's chat about number 5. This bear is just, you know, Timmy's pet bear sitting static here. What you want to do first is define our system here, and I would just define it like this. Just include the bear. And now you draw a free body. Now it's a light beam, meaning we will ignore the weight of the beam for this problem. You have a 900-pound force vector for the weight of the bear, you know, so draw that in. And remember, these forces have a line of action. You can put it anywhere up or down. We have right here, a string pulling up. I like to call that tension something like T sub L for the tension on the left-hand side of the beam. We got another one right here. I would call that a T sub R for the tension on the right-hand side of the beam. Now, one thing about those force vectors when you draw them in, there's no reason to have that force vector like equal to the length of the rope. They don't really have anything to do with one another. Just put that force vector in, maybe something like this, and move on. Now, once you get your free body complete, there should be 3 forces on it. This problem cannot be solved with force alone because it has 2 unknowns. So what I suggest is write a torque equation. The beam is in equilibrium, so the net torque is 0. Start by the left-hand side, you know, so write out the sum of all torques, and then put like maybe left end equals 0 because this is an equilibrium problem. And you've got a force vector here times this distance clockwise. You should have another force vector on the right times this distance. And the tension in this rope will not create a torque about the left end. When you put the force vector in, you should see why. So again, I don't want to draw the free body. It's your homework, but that should get you through that problem. So I'm going to go ahead and kind of call that done and call this video done as well. So I hope that this helps you out with those problems. The first 5 anyway. Have a great day.